as soon as the recommendation progresses, also the research progresses, and the outcome is that the FEC eventually will cost $2 or $3, because when you have obtained the chip, the reproducibility of the chip is very economic, so that now whatever system you buy, you will have the possibility to use the FEC. The FEC is a resident feature of the system. This is the application. This is the application table, which means that the system which have been specified are those appearing in the table, which means they are all non-return to zero. They are 2.5 gigabit per second, which means SDH or OTU1. One of the first slides I showed you in the morning was the construction of the optical channel. In the construction of the optical channel, I take a 2.5 legacy SDH system, I put some overhead, and I get what is a OTU1, which really, instead of a 2.5, is 2.65 or 2.8. It depends on the overhead. And the same applies to OTU2, which is the 10 gigabit per second system in the optical channel instead than in the SDH. As you can see, all the systems have a version with the dispersion compensator or without dispersion compensator. Well, these are the parameters that influence the choice of the application code, which means the choice of the system to be installed. Most of them are straightforward, like the bit rate or the fiber you have installed, or the wavelength range, which means C-band or L-band or S-band. The new entry is the requirements of the WDM link on the spectral excursion of the transmitter. What does it mean? It means simply that in the best of possible world, the laser transmitter is at a fixed lambda, is not moving. In the real world, the laser is oscillating around the central frequency, and this can cause some impairments when traversing devices like optical multiplexer, optical demultiplexer, and add drop multiplex, which are wavelength sensitive. What I mean is that in an optical multiplexer, like this is built for having lambda 1 on this port, but it has a filtering window, and if the lambda moves in this window, the power will be reduced. I have an optical filter which is done this way, and I enter with lambda 1, and this is the optical power. If lambda 1 is oscillating, it arrives here, the power is reduced. so that all the lambda sensitive devices need to have very stable transmitted wavelength, which means that requirements are put over the laser stability.
Suppose that you have many SDH system, which you want to be transported in DWDM system. Then, when at different ports or different interfaces, you put the SDH system like 10 gig or 2.5 gigs. Are they going to be transported on same wavelength or at different wavelength when they enter in DWDM system?
I am not sure I have well understood your question. I will try to reply, and if I did not understand you, we will have a next round. Well, WDM is transparent, which means that in the same multiplexer, you can have mixed signal, which means that you can enter the first lambda with 10 gigabit per second, the second one with 2.5, and so on. This is the easiest way to perform SDH connection. But if you use optical channels, you can use the same lambda, for example, to transport 4 2.5 gigabit per second system. They are mixed, they are multiplexed inside the optical channel system. So you enter with 4 systems and you get out with just 1 lambda. This can be done only and only if all the 4 flows are going to the same destination. Because anytime you put electrical signal inside the optical wavelength, you will transport as an optical wavelength. You will not have any more optical switching. What you can do is, at some point in the network, to have all the lambda out in an optical add-drop multiplex. You have the lambda dropped, you demultiplex, you extract the electrical signal you need, and then you put again the 3 remaining in the lambda going eventually with another 1. But the switching can be made only at electrical level. But if you want to reach the same destination, you can put in the lambda and forget them. Was it the right answer? Okay. Backbone networks. We have arrived to the inner part of the network. This is the geographical part of the network, which is devoted mainly to long distance. It may be another country after the border. It may be another continent after the ocean. So we start from several hundred kilometers and we end with several thousand kilometers. Well, now we have applications running a lot of channels high bit rate, we are in the core. We have to expect only longitudinal compatibility. If you have 80 channels, it's really impossible to respect all the parameters, to have a system from different vendors interconnected in a transverse way. What you can do is only to have a longitudinal compatibility. I remember what is longitudinal compatibility. This is France. This is Greece. You want direct link from France to Greece. You have two systems from different vendors. They are able both to perform the task, but separately. You can mix on the same link different systems from different vendors, but you cannot mix them. This is longitudinal compatibility. They have the same span with the same performance and so on, but you cannot mix them. Since, again, I repeat, we are in the presence of very many channels, can be 40 or 80 channels. We are in the presence of different other aspects. You can have only longitudinal compatibility. Pay attention, longitudinal compatibility means only I have to transport a given number of channels at a given bit rate for 1,000 kilometers. I don't mind which wavelength the vendor will use. Some vendors will use wavelength in the C-band. Other vendors will use wavelength in the L-band or in the short band. And the way they will put amplifiers of different type. But I want only a number of channels at a given bit rate for 1,000 kilometers over my fiber. So I will tell the vendor I have G655 fiber. So your system should operate according to my fiber. Yes.
And here it's greater than or equal to 1,000.
So I'm not sure I well understood your question.
Yes, I repeat.
Yeah.
In metro core,
yeah.
the
distances are up to 400.
Up to 400.
Yeah.
But for the long haul, it is greater than or equal to 1,000.
Greater than 1,000?
Greater than or equal.
More than?
It's greater than or equal. In slide 82, I think. So, but my question is, how do you now classify a distance between 400 and 1,000? Say 600 kilometers.
Well, the 1,000 distance is the objective distance, which means that systems are built to cover 1,000 kilometers. But you can still use them for 600 or 700 or 550. You can use them on shorter distances, if I have well understood. The question was, there is a region between 400 and 1,000 which is not covered. But you can use 1,000 system to cover 500 or 600 connections. No, it's more than, they are defined for more than 1,000 kilometers, but you can use them on shorter distances. What is very important in this picture, which, by the way, misses the optical fibers that are going here. Transportation between different programs computer programs does not work very well. Well, points to be noted. After the multiplexer, we have an optical amplifier whose name is booster amplifier. After we have optical line amplifier, which are amplifiers distributed along the path. Normally, they need only a power source. They can stay in the land. The only thing you should have the power feeding to feed them. At the other end, the DMUX, in front of the DMUX, we find a preamplifier. This is the reference scheme. Of course, you don't need every time a booster amplifier, or you don't need a preamplifier in some cases. In some other cases, you don't need neither of them. This is a multi-span, and as I told you in the morning, the number of the span could be, in this situation, 5 or 6 because of noise introduced by optical amplifier. I repeat, only longitudinal compatibility is provided by G696.1 because of the complexity of a link. And moreover, the design of a very long haul system, high bit rate, many channel, is not very easy. From my experience, I have to say that nobody designed such a system with a sheet of paper and a pencil. It is normally done by means of computer programs that are able to calculate the needed parameters. What I mean is that going again to the reference, what I mean is that in the fiber, here, you have many channels, high power, which means nonlinear effects. In the presence of nonlinear effects, you are not able to say what will be the final results. I will explain in a second. Suppose you have here 40 channels, each one carrying 1 milliwatt of optical power. So in total you have 40 milliwatt of optical power, and your reach is 500 kilometers. In a linear regime, if the 1 milliwatt is increased to 1 milliwatt and half, I should expect that the reach will increase as well. This is normal operation. I have the BTS tower, the cellular phone tower. If I need to cover a region larger than the design region, I increase the power of the transmitter. Until I am in a linear regime, this works. For optical system, when the power increases above some tens of milliwatt, I am not sure that increasing the power will increase the reach. Maybe the performance will be degraded and the reach will be decreased. This is because I am in a linear regime. What can be done? Well, normally the vendor has a suitable simulation program. He puts all the data in the simulation program and he gets the result. The result could be to have the maximum reach, to have 500 kilometers, 1 milliwatt, 0.9, 0.8, 1.2, 1.3, 1.1, 0.7. So the final result could be a fine-tuning of the parameters. And those parameters will be the parameters then that give you the maximum reach. This is what we call nonlinear regime. And this is the meaning. This is the meaning of this last sentence. The vendor will take care of the simulation. The vendor will ensure that the performance objectives are met, but please don't mix system of different vendors on the same long haul line, because very often they will not work at all. Again, we define some client class, which is the client bit rate before entering the optical channel, as we saw in the morning, and before any FEC is added. The specifications are organized again according to application codes, which take into account various parameters. For the first time, we saw the use of bandwidth, optical bandwidth, different from the conventional one. We saw the large bandwidth. So one of the parameters is the bandwidth we are going to use, the number of channels, which kind of client we are transferring to the destination, which is the span, the number of amplifiers, it is not in the list, but it's very important, and the type of fiber that are to be used. Since understanding or writing the application code is a very boring operation, I have left an example of application code just for the last application, which is long haul. And this is the application code of system for long haul network. N is the maximum number of channels, so that it could be 40.40G, which means 40 channels at 40 gigabit per second, dash 5 spans. Then we have the W letter, which means it's a short haul application or a very long haul application, 33 dB. After the fiber, which can be 652A, 652D, and so on. And afterwards, between brackets, the operating wavelength range in terms of spectral band. Now we have the classification of spectral bands. This is the conventional, just around 1550. This is the large bandwidth, short, original, which means second window, around 1300. And this is the extended bandwidth, which is between O and S, and has been made possible by the new fiber types. This is an example of application code, 40-channel system, 10 gigabit per second payload, 20 long haul span on a conventional fiber. In the C band, the last letter R is the fact that the link is powered by means of Raman amplification. We shall see what is Raman amplification in a few seconds. No. Well, what is Raman amplification? Raman amplification is a kind of amplification which take place in the transmission fiber itself. I have the transmission fiber. I inject very high power light from one end at a suitable wavelength. The energy will be coupled to the incoming signal, and the signal will be amplified. This is an optical Raman amplifier, but yes, I remember well now, we shall have the opportunity to consider Raman and distributed fiber amplifiers tomorrow morning when dealing with the submarine cable. Well, for the time being, I will stop here. I beg your pardon if some parts were a little bit boring. And if there are any questions, I am ready to answer and willing to answer if I can, of course.